Hello, ma'am.
Good evening, sir.
Yeah, ma'am.
Yes, sir, you can start, sir.
Yeah.
Good evening, sir.
Good evening. Ajay is not joining, ma'am.
Sir, he got 104 fever, sir.
Oh, take care, ma'am. Take care.
Hello, ma'am.
All right, then Lakshmi will continue and we'll finish off today this chapter possibly. Right. Yesterday we were learning with, not yesterday, the last class we were learning with some of the questions based on valence bond theory and also based on crystal field theory. We'll continue with that topic. I think 25 questions we did. We'll continue from the 26th question. Now, which of these statements about CO and Cn 6 times 3 minus is true? CO, Cn 6 times 3 minus is true. Now, the first option is CO, Cn 6 times 3 minus has no unpaired electron and will be of low spin configuration. COCN63 minus has 4 unpaired electrons and will be in low spin configuration. COCN63 minus has 4 unpaired electrons with high spin. COCN63 minus has no unpaired electrons and will be high spin. Now we need to work out this. This is based on crystal field theory. It is not based on valence shell electron pair repulsion theory. This problem is based. Now in the complex COCN6 3 minus. As a whole, the charge is -3. Cyanide is a monodentate ligand. -1 into 6 is -6. Cobalt is X, so X will be equal to +3. The oxidation number of cobalt is +3. When oxidation number of cobalt is +3, the electronic configuration of cobalt is argon configuration and 3d6. Argon configuration and 3d6. I'm writing the electronic configuration directly of the oxidation state. Remember, now in case of what the strong field ligand, what happens? Pairing takes place. Cyanide is a strong field ligand. Since cyanide is a strong field ligand, what takes place? Pairing of electrons takes place within the central metal. Now, if we draw a d orbital like this, we know that d subshell has 5 orbitals, 3, 4, and 5. Since it is d6 system, we write 1, 2, 3, 4, 5, and 6 system, 6 electrons. Now what happens is when the ligands approach the central metal atom or ion, what happens? Crystal field splitting will take place. Since it's an octahedral complex, you will have 3 orbitals at the lower energy level and 2 orbitals in the higher energy level. This is called as EG level, and the lower energy level is called as T2G level. Now here we have 6 electrons. Since we have 6 electrons in the d orbital, the first electron enter orbitals with parallel spin, but remaining may be paired up in T2G level, giving rise to a low spin complex. Now 6 electrons are there. There's a possibility 1, 2, 3, 4, 5, and then coming to 6. It's not that way, because lower energy has to get filled first, only then higher energy gets filled. Since we have 6 electrons, 3 and 4, 5, and 6, pairing of electron within the metal takes place. Now, since the pairing of electron within the metal takes place, now this is called as a low spin complex. It is called a low spin complex. And when we say it is a low spin complex, do you have any unpaired electrons? Do we have any unpaired electron? You can see here, there is no unpaired electrons. All these are paired up electrons. Low spin, and it is what? No unpaired electrons. Therefore, the answer for this question is option A. So COCN63 minus has no unpaired electrons and will have a low spin configuration. Hence, the answer for this question is option A. Followed. Did you follow, students? Are you there?
Yes, sir. Followed.
Yeah, the next question is the 27th question. In which of the following coordination entities the magnitude of delta naught crystal field splitting energy in octahedral field will be maximum? Atomic number of cobalt is 27. Remember, in all the cases, the central atom is cobalt. In all the cases, the central atom is cobalt. Now, when it is an octahedral complex, here also it's 2 or 6 times, it's printing mistake, typing mistake. So D subshell, if you take, it has 5 orbitals. Now, when this undergoes the splitting into T2G level and EG level, T2G level and EG level, this splitting energy is represented as delta. And this not indicates it's an octahedral complex because the coordination number is 6 overall. Therefore, coordination number is 6 for all. Therefore, it's an octahedral complex. Now, the question they're asking is, which of the following coordination entities the magnitude of delta naught, that means crystal field splitting energy in octahedral field, will be maximum? See, crystal field splitting energy will be maximum for the complex in which the ligand is a strong field ligand. See, all the complex contain central metal atoms same, coordination number is same, but the ligands are different. So cyanide is the strongest ligand here, strong field ligand here compared to all the other. Since cyanide is a strong field ligand, the crystal field energy delta naught will C and will be option C. Later will be the crystal field splitting energy, right? Hence the answer for this question is option C. Followed, students? Yeah?
Yes, sir.
Yeah.
Yes.
The next question, chromium complex it is. CrH2O 6 times. CrH2O 6 times Cl3. Atomic number of chromium is 24. And has a magnetic moment of 3.83 Bohr magneton. 3.83 Bohr magneton. The correct distribution of 3D electrons in chromium of the complex is. Now see, they've given the magnetic moment as 3.83. Since they've given you the magnetic moment 3.83, we can find the number of unpaired electrons. The Bohr magneton, magnetic moment is given by the formula mu is equal to square root of n into n plus 2. So simplifying this, you can write 3.83 into 3.83 will be equal to n square plus 2n, squaring both the sides. That's all I've done. So on simplification, you will get the n value approximately to be what? The 3. N value approximately to be 3. Now, since the number of unpaired electrons in D is 3, now what will be the electronic configuration? Chromium atomic number is 24. The electronic configuration of chromium is argon configuration 4s1 and 3d5. But here the chromium charge is what? Plus 3. Since the charge on chromium is plus 3, 1 electron from here and 2 electron from here will be lost. Therefore, chromium 3 plus will have the electronic configuration, argon configuration, and 3d3. It has 3d3. So therefore, the distribution of electron will be, what will be the distribution of this electron? Now, in order to understand the distribution of electron, we have to write the d orbitals like this 5. It will undergo splitting to form 3 with lower energy T2G and 2 with higher energy EG. Since we have 3 electrons here, 1, 2, and 3, this 3 electron will get filled in T2G level like this. So that means 3dxy1, 3dyz1, and 3dzx1. This is x square minus y squared, 3d x square minus y square, and this is 3d z square. This is the names of the atomic orbitals. So what will be the answer? The answer for this question is option D, xy, yz, and zx. So option D. The next question, crystal field stabilization energy for high spin D4 octahedral complex is. See, in case of high spin complex, delta naught will be small. When will be high spin? See, high spin is possible when we have a weak field ligand. Weak field ligand. When we have a weak field ligand, then the complex form will be high spin. In case of weak field ligand, delta naught will be a smaller value. Crystal field splitting energy will be small. If you have, if you're talking about low spin complex, in low spin complex, the ligand will be strong. Remember this, it's opposite, strong field ligand. Whenever we have a strong field ligand, crystal field splitting energy will be extremely high. Delta naught will be high. Now they're asking crystal field stabilization energy of high spin D4 octahedral complex. High spin means what? Weak field ligand. When weak field ligand, delta naught value will be smaller. That means the energy required to pair up the fourth electron with the electron of the lower energy d orbital would be higher than that required to place the electrons in the higher d orbital. Thus, pairing does not occur for higher spin d4 octahedral complex. So what do you mean by that? Meaning, if you have a d orbital here, we have 5 d orbitals. This will split into what? Eg level and T2g level. Now what happens is, since it is a D4 system, it means we have 4 electrons here, 4 d electrons, therefore it's called as D4 system. Now since it is a high spin complex, what happens is delta naught is small. That means this energy level is small. This delta naught value is small. Since delta naught value is small, what happens is the 3 electron gets filled here. Instead of the 4th electron getting filled here, it will go to a higher level. Why? Because delta naught is small here, because it is a high spin complex. So this will be the electronic configuration. This will be the representation. Now they're asking crystal field stabilization energy. Now in order to calculate the stabilization energy, crystal field stabilization energy, the formula what we will be using is, now delta naught value I gave you for T2G, it will be minus 0.4 I gave you, and this is plus 0.6 delta naught I gave you. So it will be 3 into minus 0.4 plus of 1 into 0.6. So it will be minus 1.2 plus 0.6. That will be equal to minus 0.6 delta naught. The answer for this question will be option D, minus delta naught, minus 1.6 delta naught. Followed with this question, crystal field stabilization energy, students?
Yes, sir.
Yeah. Now coming to the last part of this chapter, today we'll try to finish this chapter. Oh, this I didn't teach you, I'll teach you this. It is not there in your syllabus, but anyways, we will learn effective atomic number. This effective atomic number, it's otherwise called as Sidwick theorem. What is this effective atomic number? Now, it is called as EAN rule. It's also called as effective atomic number rule. We will understand effective atomic number rule, and then we will learn how to calculate the effective atomic numbers. This is not there for your 12th standard, but it will be useful for your competitive exam. You have to just learn the formula so that we can calculate the effective atomic numbers of different complexes. Now, what is this effective atomic number rule? The effective atomic number rule is the central EAN rule. I will write EAN rule. Effective atomic number rule. The central metal atom or ion keeps on accepting electrons, donated by the ligands, until it reaches the nearest noble gas configuration. So what is EAN rule? EAN rule is defined as the central metal atom or ion will keep on accepting electrons donated by the ligands until it reaches the nearest noble gas configuration. Noble gas configuration. That's called as what? EAN rule. We will take an example. Before we understand the example, EAN is calculated by the formula Z minus X plus Y. Now, what is this Z? Z is called as atomic number. X is what? The oxidation number. And Y is the number of electrons donated by the ligands. So Y is number of electrons donated by the ligands. That's the formula to calculate the effective atomic number, Z minus X plus Y. Now, coming to some of the examples here, we will learn here. See, in order to stabilize to stability of the complex, we proposed effective atomic number. EAN generally coincides with the atomic number of the next noble gas configuration. I clearly told you, the central metal atom or ion keeps on accepting electron until it reaches the nearest noble gas configuration. See the formula here. Effective atomic number is given by the formula atomic number minus oxidation number into, I told you, number of electrons donated by the ligands. Number of electrons donated by the ligands. You can otherwise write it as plus of coordination number into 2. Coordination number means number of monodentate ligands bonded to the central metal atom. Each ligand donate 2 electrons. Therefore, it can be written otherwise coordination number by 2. All right. Both means same. We'll work out. Some of the examples we will take and work. Few examples, and then we'll go to the next concept. K4FeCN6. Calculate the effective atomic number of iron in K4FeCN6. See, this is with respect to iron. Now, in order to understand this, as a whole, the charge is 0. Cyanide is -1 into 6 is -6. Cobalt, iron, we don't know the oxidation state X. Potassium is +1 into 4, 4. So X will be equal to +2. Oxidation number of iron is +2. We need to calculate because EAN is given by the formula Z minus X plus Y. Z is atomic number 26. X we found out to be 2 here, -2. Plus, what is Y? Coordination number is 6. Coordination number into 2, or each ligand donate 2 electrons. 2 into 6 is how much? 12. Therefore, it will be what now? 36. Therefore, it will be 36. 36 is the krypton electronic configuration. Now, you should ask me a question. Why K4FeCN6? It can be FeCN7. No? It cannot be 7. Because once we have 6 cyanide ions approaching the central metal, it becomes a nearest noble gas configuration. Noble gas configurations are highly stable. Therefore, further it will not accept electrons. Did you understand? That is why I was giving you the statement here. Central metal atom or ion keeps on accepting electrons donated by the ligands until it reaches the nearest noble gas configuration. Once it reaches the nearest noble gas configuration, it attains what? Stability. So this is the formula to calculate the effective atomic number. One more example we will take. CuNH3 4 times SO4. Now you have to calculate the effective atomic number. Now, in order to calculate the effective atomic number, as a whole, the charge is 0. Sulfate is -2. Ammonia is a neutral ligand, 0. Copper, we take it as X. So X will be equal to +2. Oxidation state of copper is +2. Atomic number of copper is 29. Oxidation state of copper is +2. But since the formula is minus here, minus into plus is what? -2. Plus of, we have how many ligands? We have 4. Each ligand donate 2 electrons. Therefore, it will be 8. So it will be 27 plus 8. The nearest noble gas configuration is 35. See, 36 is the krypton configuration. But even though it accepts 35, further 2 electrons it will not accept. Because each ligand donates 2 electrons. So this is a stable effective atomic number for CuNH3SO4. If you take a molecule like this, K3FeCN6, potassium ferricyanide, common name. As a whole, the charge is 0, -1 into 6 is -6, iron is X, and potassium is +1 into 3. X will be equal to +3. Oxidation state of iron is +3 here. What will be EAN for this? EAN will be Z minus X plus Y. That is 26 minus 3 plus of, again, 12 electrons. 6 ligands, no? 6 into 2, 12. So it will be 23 plus 12. It will be 35. Did you understand? Students, are you following?
Yes, sir. Following.
Yeah, now few more examples I'll give you. NiCO4 times. This is tetracarbonyl nickel. It's a neutral complex. When we say it's a neutral complex, as a whole, the charge is 0. Carbon monoxide is a neutral again. 0 into 4 is 0. Nickel is X, so X will be equal to 0. Now, what is the effective atomic number of nickel here? So effective atomic number of nickel will be Z minus X plus Y. Nickel is 28. Oxidation number is 0. But how many ligands we have? 4. 4 into 2 is what? 8. So what will be this? Total atomic number of electrons will be 36. Did you understand? So you can see there are so many other examples given here in this chart. So I have worked few. There's some more examples given. See, try to remember the atomic numbers. See, for a silver, atomic number is 47. At least till 30 elements you know in the periodic table. Silver you should know. Platinum also you should know. I think platinum it is 78. Atomic number is 78, I believe. Or they may give in the exam. But try to remember for platinum, silver, and at least till 30 elements. This is with respect to the effective atomic number with respect to coordination compounds. Now, the stability of the complex. Factors affecting the stability of the complex. And first one is nature of the central metal ion. There are complexes, reasons we learn, but we want to simplify that here. Right, factors affecting the stability of the complex ion. First one is central metal ion. The higher the charge density on the central metal ion, greater is the stability. Higher the charge on the central metal ion, greater is the stability. For example, you can see here the ion is Fe2 plus. Here the charge of ion is plus 2. Here the charge on ion is plus 3. See the K value. See the K value. In case of the ion with plus 2 charge, the K value is 1.8 into 10 power 6. But when the ion is having plus 3 charge, here it's 1.2 into 10 power 31. This is large, higher. So this is more stable. So charge on the metal ion, if it is greater will be its stability. The first point is nature of the central metal. Higher the charge density on the central metal, greater is what? The stability. Did you follow the first point?
Yes, sir.
Yeah, the next one is nature of the ligand. The second factor affecting the stability is nature of the ligand. Greater the base strength is the ease with which it can donate its lone pair of electron, and therefore greater is the stability of the complex. So nature of the ligand, greater the base. All ligands are Lewis base. All ligands are Lewis base, meaning all ligands will donate what? A pair of electron. Greater at which the ligands donate electron to a central metal, stronger will be what? Greater will be what? The stability. Here you can see copper complex cyanide. Here it is ammonia. Here it's 2 into 10 power 27. Here 4 into 10 power minus 11. So cyanide ion is a stronger ligand compared to ammonia, because cyanide will donate much easier electron pair compared to ammonia. So the second one is nature of the ligand. Greater the base strength. Why we call it as base strength? Because all the ligands are Lewis base. That is why we call it as base strength. So if the base strength is more, then stronger will be, or stable will be the complex. The third one is presence of chelating ligand. What is a chelating ligand? Chelating ligand means a ligand which can form a ring will be called as chelating ligand. A ligand which can form a ring with the central metal atom is called as a chelating ligand. So chelating ligands or complexes are more stable than a non-chelating ligand. So nickel ammonia here. See, ammonia is not a chelating ligand. Ethylene diamine is a chelating ligand. Therefore, you can see chelating ligand forms more stable complex as compared to that of monodentate ligands. So this is more stable compared to ammonia complex. The next one is spectrochemical series. This is an important question for 12th standard. What is spectrochemical series? Arrangement of ligands in the increasing order of their strength is called as spectrochemical series. Ligands can be arranged in increasing order of their strength. and the series so obtained is called as the spectrochemical series. Now you can see halogens are on the extreme left. Halogens are weaker field. I minus is lesser than bromide, chlorido, fluoride, hydroxo, oxalato, water, pyridine, ammonia, ethylene diamine, nitrite, cyanide, carbon monoxide. Amongst all this, carbon monoxide is the strongest. Next comes what? Cyanide. So arrangement of ligands in the increasing order of their strength is called as spectrochemical series. Remember, for 2 marks in your 12th standard. Now ligands arranged to the left to ammonia. Ligands arranged left to the ammonia are regarded as weaker ligand, which cannot be cause forcible pairing of electron. That means it will not cause forcible pairing of electrons within the, it will not go against what? The Hund's rule within 3D level, and thus form outer orbital octahedral complex. On the other hand, ammonia and all ligands lying right to it are stronger ligand, which forms inner complex, octahedral complex, after forcibly pairing. So when the strong field ligands are there, what happens is pairing of electrons within the central metal will take place. So weak field ligand, strong field ligand, differentiation is given based on the spectrochemical series. So ammonia is considered to be the center point. Before ammonia, what are ligands you have? They're all weak field ligands. So it will not force the pairing of electron to take place within the central metal. Now, after ammonia, what all ligands are present? They all are called as strong field ligand. These are called as weak field ligand. So they will force the pairing of electron to take place. All right. Now, preparation and application of coordination compounds. So the coordination compound application you should know. All right. They can ask you a question for 2 marks in your PUC, or they can ask you some of the competitive questions are there here. We will learn. Preparation. Coordination compounds are generally prepared by the application of the following methods. The first one is ligand substitution reaction. Ligand substitution reaction. Now, copper sulfate solution. Copper sulfate solution, meaning copper sulfate, when you dissolve it in water, we all know that it dissociates to form water and SO4 2-. That is what we have been learning. But actually what happens is this copper ion which is formed will react with water, because water is behaving like a ligand. Water can donate a pair of electrons. So therefore it forms a complex like this, water complex like this. See, that is why it is written as light blue color here, CuH2O4 times 2 plus. So it is, now we'll have to understand that any salt when dissolved in water, the respective ions are not formed. They will have its complex also, because water can behave like a ligand. This is light blue. To this copper water complex, if you add ammonia, ammonia being stronger than what? Water, it will displace water. And you can get CuNH3 4 times 2 plus. Therefore, you get a deep blue color, a dark blue color. So you can prepare complexes by ligand substitution reaction. Here, what's happening? For water, which is a ligand, there is ammonia which has been substituted. Therefore, you get a deep blue complex. That's the first method. So we can prepare a complex by ligand substitution method. Second one is direct mixing of reagent. Direct mixing of reagent. See, platinum dichloride, PTCl2, is allowed to react with ethylene diamine. When PTCl2 is allowed to react with ethylene diamine, you get PTEN twice Cl2. PTEN twice Cl2. That means a complex is formed here. So this is a salt. This is a salt. When the salt is allowed to react with ethylene diamine, a compound, you get a complex. Therefore, it's called as direct mixing of reagent. Third method of preparing a complex is by redox reaction. Now, in this reaction, either oxidation or reduction is involved. Cobalt nitrate is allowed to react with ammonia and ammonium nitrate and hydrogen peroxide. See the complex. So what happens is you get CO, NH3, NO2, and NO3 twice. This is the complex you get. So this, see, we can prepare a complex by 3 methods. One is ligand substitution reaction method. The other one is by directly mixing the reagents. And third is by redox reaction. So these are 3 methods of preparing a ligand, what's a complex. Now, what are the applications of complex? This is important application. The first one is estimation of hardness of water. Hard water, soft water, you would have heard. Hard water will not give lather with soap. Soft water will give lather with soap. Hard water is because of the presence of calcium and magnesium salts. Due to the presence of calcium and magnesium salt, the water becomes harder. Calcium carbonate, magnesium carbonate, calcium sulfate, magnesium sulfate, all right? They are the reason for water to be hard. Hardness is due to the presence of calcium and magnesium salts. There are 2 types of hardness. One is temporary hardness and the other one is permanent hardness. This temporary hardness is eliminated by boiling the water. You would have observed when you boil the water for a long time, you can see some solid particles, which is in the form of a layer settling on the top surface of the water. That is nothing but what? Carbonates of calcium and magnesium, which can be skimmed off, removed and filtered, or which can be filtered. So temporary hardness can be removed by boiling. Permanent hardness cannot be removed by boiling. Permanent hardness is removed by chemical methods. Now, when we say chemical methods, one is ion exchange method. Ion exchange method. Ion exchange method. All right. Now, that is not our concern. The concern is with respect to the coordination compound. Now, what is that application we're talking about? Estimation of hardness of water as calcium and magnesium ions from complexes with EDTA. Now, this calcium and magnesium ion, I write it as Mn plus, calcium 2 plus or magnesium 2 plus, you can write. Now, this hard water is taken in the conical flask. To that, you add an indicator, EBT. This indicator is called as eriochrome black tea, EBT, eriochrome black tea. When you add eriochrome black tea, you get a wine red color, wine red color. This is in the conical flask. To this, you titrate against EDTS, ethylene diamine tetraacetic acid, which is taken on the burette. EDTA is stronger ligand, it will displace EBT. Therefore, what you get is you get metal EDTA complex plus giving you free EBT. This free EBT is a clear blue color. Clear blue color. The end point is wine red to clear blue. It's a titration. This kind of titration is called as complexometric titration. This kind of titration is called as complexometric titration. See here, when you add EDTA to manganese, metal, calcium and magnesium will bond with EBT to form a wine red complex. And that when you titrate against EDTA in the burette, what happens? EDTA stronger ligand displaces EBT. So EBT gives you free EBT, therefore the clear blue solution you will get. So by titrating EDTA with the hard water, we can find the hardness of water. That is the first application. Animal and plant world, example, chlorophyll is a complex. In chlorophyll, magnesium is a metal present. Presence of magnesium gives you green color to chlorophyll. And in animal, hemoglobin is a complex of iron. The red color of the blood is because of hemoglobin. Hemoglobin contains iron. And remember, iron is in +2 state. It's not in +3. Remember, iron is in +2 oxidation state in hemoglobin. And vitamin B12 is a complex which contains cobalt 2+. So most of the metals are having complex. Enzymes are also containing metals. Remember. So animals and plant world, chlorophyll is green because of magnesium. Hemoglobin is red because of the complex of iron. And likewise, vitamin B12 is the complex of cobalt 2+. Next is electroplating. Electroplating of metal involves the use of complex salt as electrolyte. See, electroplating, what do you mean by electroplating? By passing current, coat a layer of metal on the required metal. For an example, if iron, now you would have seen the two-wheelers vehicle, the rims of the vehicle, it is not steel, it is electroplate. It's made of iron, which is coated with a layer of what? Zinc or aluminum or chromium, whatever. It's chromium in general. Those kind of things are called as electroplating. So if you have to coat a layer of silver on any metal, then the process used is called as electroplating. So complex are used. Extraction of metals. Gold and silver are extracted from the ore by dissolving sodium cyanide, dissolving in sodium cyanide. So what happened? Gold and silver is a noble metal, which are not soluble in acids or bases. They are soluble in cyanides. When gold and silver are dissolved in cyanide, you get gold complex or silver complex. So that's the application, one more application. Detection and estimation of metal ions like nickel 2 plus using dimethyl glyoxamine. So estimation of nickel also is done by a complexometric a complex formation. So therefore, that's one more application. This is important. Medicine. Cisplatin. Cisplatin. What is cisplatin? This is cisplatin. It's a square planar structure. Square planar structure. Cisplatin. So this is used for the treatment of cancer. So cancer cells are prevented to grow by using what? Cisplatin. Application of cisplatin. Right. And some of the next part of the topic, last part of the topic, it is called as organometallic compound. It's called as organometallic compound. What do you mean by organometallic compound? If a metal is bonded to carbon atom directly of an organic molecule, then those are called as organometallic compounds. What do you mean by organometallic compounds? Organometallic compounds are compounds in which metal is directly bonded to carbon atom of the organic group. These are compounds in which metal atom or metalloid or non-metal atom like boron, silicon, phosphorus, etc. is directly linked to carbon atom of the hydrocarbon radical. So metals, non-metals and metalloids, if they are attached to carbon of the hydrocarbon, then they are called as organometallic compounds. A simplest example for organometallic compound, you would have heard Grignard reagent. You would have Grignard reagent, RMgX. You can see magnesium is directly bonded to R group. R is nothing but alkyl group, hydrocarbon radical. So whenever the metal is directly bonded to carbon atom of the organic group, then they are called as what? Organometallic compounds. So organometallic compounds contain at least one metal carbon bond, metalloid carbon bond, or non-metal carbon bond. So we will concentrate mostly on metal carbon bonding. So here you can see, I gave you the Grignard reagent example. It's written here, C2H5MgBr. You can see here, this is metal and this C2H5 organic part, diethyl zinc. Likewise, so many other complexes here they're mentioned. So organometallic bond, magnesium carbon in the first case. Here it is zinc and carbon in the second case, titanium and carbon in the third case, and here it is silicon and carbon. Silicon is a metalloid here, silicon and carbon. So classification of organometallic compounds. Organometallic compounds are classified as sigma bonded organometallic compounds. Compounds such as RMgX, R2Zn. R2Zn is this. R2Zn. This is the general representation. R2Zn. Are you following, students, what I'm trying to tell now?
Yes, sir.
Yeah. Called as what? Sigma bonded organometallic compound. The other one is pi bonded organometallic compound. When we say pi bonded metallic compound, the transition metal binds to the unsaturated hydrocarbon and their derivatives using their d orbital. Here, metal atom is bonded to ligand in such a way that donation of electrons and back acceptance of ligand is feasible. This is called as pi orbitals of ligand. These are called the pi orbitals of ligand, and these are called pi complexes. Example, pi cyclopentadienyl ion complex, ferrocene, Fe eta 5 C2H5 C5H5, just C5H5 twice, all that, it's a sandwich compound. You can see here, this is ferrocene. This is cyclopentadiene, right? This is a pentagon. It's a pentagon like this, pentagon. Or maybe you could write 3 bonds. And this is another pentagon here. And these are unsaturated, which is bonded to iron here. Pentagon, when we have a double bond here, due to resonance, what happens? The pi bond shifts. It is ferrocene. Likewise, you can see here, this is this complex. No, that's not written here. It's not written here. This is potassium trichloroethylene platinate 4. See, potassium. No, here it's also. Where's it? Potassium. Potassium is K plus. It should be outside. It's called a Z salt. Potassium K plus. Trichloro. 3-chloro we have. Ethylene we have. Platinate 4. This is also an example for organometallic compound. Ferrocene. Next, complexes containing both sigma and pi bonding character. They are called as metal carbonyls. See, metal carbonyls are there in your exam. Now, carbon monoxide, if you say carbon monoxide will have CO and also you'll have few orbitals like this. Now, we all know that metal ligands donate the electron to the central metal. Electrons are donated by the ligands to the central metal. Now, in case of metal carbonyls, what happens is not only the metals are donating, ligands are donating the electron to the central metal. Likewise, metals also will donate electron to the ligand, empty orbital of the ligand. Therefore, this is also called as back bonding. Back bonding. It is also called a synergic effect. It's also called a synergic effect. What is the synergic effect? Now, generally, so far, what we have been learning is electrons are donated by the ligand to the central metal. But in case of neutral complexes like NiCO4, FeCO5 types or CO56, not only the ligands donate electron to the central metal, but also metal electrons in the outermost orbit of the metal. Those electrons will be donated to what? The empty orbitals of the ligand. Therefore, this is sigma bond and this is pi bond. So back bonding, it's called as what? Back bonding. See here, complex containing both sigma and pi bond characteristic. Sigma characteristic due to the donation of ligand to the central metal. Pi characteristic because of electrons of the metal donating to the empty orbitals of the ligand. Followed, applications of organometallic compound. Grignard reagent is one of the application of the organometallic compound. Grignard reagent can be used extensively for synthesis of any organic compound. Using Grignard reagent, we can prepare alkanes, alkenes, alkynes, alcohols, ethers, esters, any of the organic compound. That is the advantage of Grignard reagent. That is why a scientist, Grignard, gets a Nobel Prize for his findings. Next is Wilkinson's catalyst. Wilkinson's catalyst is PHP3RHCl. Tris triphenyl phosphine, rhodium is a metal, RH is rhodium, chlororhodium 1, and it's used as homogeneous catalysis for hydrogenation of alkene. Wilkinson catalyst is used as a catalyst for hydrogenation of alkenes. Next is Ziegler-Natta catalyst. It's a composition of transition metals, titanium tetrachloride and trialkyl aluminum, and it is used as heterogeneous catalysis. So Ziegler-Natta catalyst is used as heterogeneous catalysis. Example for Ziegler-Natta catalyst is triethyl aluminum and titanium tetrachloride. Mixture of this will be called as Ziegler-Natta catalyst, which is used as heterogeneous catalysis in the polymerization of alkenes. If you have to prepare high density polyethylene, then the catalyst what they're using is Ziegler-Natta catalyst. All right, polyethylene, you know polyethylene. So last part of the topic is questions, few questions on this, and then we're going to stop with this chapter. We'll continue with a new chapter in the next class, that is possibly tomorrow. Which of the following does not have metal carbon bond? Which of the following does not have metal carbon bond? So it is OC2H5, OC2H5, and you have aluminium, OC2H5, OC2H5. You can see metal oxygen bonds here. There is no metal carbon bonds here. Therefore, the answer for this question is option A. The next one, among the following, which is not the pi bonded organocompound, which is not a pi bonded organocompound. Now, in case of this one, you have CH3 4 times Sn. There is 4 simple bond or single bond between methyl group and what? Tin. There is no pi bond here. So it will be like this: Sn, CH3, 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 and CH3. These are the sigma bonds. No pi bonds between tin and methyl group. So the answer for this question is option D. All will have pi bond. See, C2H4, CH2, CH2, a pi bond will be here. And here's C5H5. It is a pentagon. We learned ferrocene, this is ferrocene. Ferrocene, we learned it like this. We learned ferrocene like this. It is an unsaturated molecule. These are unsaturated, double bond will be there. Likewise, benzene, C6H6 is also unsaturated, double bond. So the molecule without a pi bond is option D. Which of the following organic compound is sigma and pi bonded? Which of the following compound is sigma and pi bonded? Now I cannot keep taking more time to explain this. Already we have spoken. Now carbonyls, whenever we have carbon monoxide as a ligand, remember it will exhibit sigma and pi bond character. So here the answer for this question will be CO is cobalt here, cobalt, and this CO is carbon monoxide, NH3. Since we have carbon monoxide as a ligand, back bonding is possible. Back bonding, that means in this both sigma and pi bond will exist. Therefore, the answer for this question is option C. In metal complex, carbonyl, in metal carbonyl, having general formula MCOX time, where M is a metal, X is 4, the metal is bonded to. Metal is bonded to. X is 4, they say. When we say X is 4, in metal carbonyl having general formula MXCOX, where M is metal and X is 4, and the metal is bonded to, and the metal which is bonded to carbon and oxygen, carbon monoxide, oxygen and carbon. So the answer, this is not clear for me, but the question is not clear for me, but they say the answer to be carbon here. They say it is carbon because I guess metal is like this, 5d orbitals for metal, and carbon monoxide, I told you carbon monoxide is carbon triple bond. Carbon triple bond oxygen like this, and you'll have a pair of electron. This will donate electron to the central metal, and the orbitals, the electrons of the metal are donated to the empty orbitals of the carbon monoxide to form pi bond. This is pi bond and this is sigma bond. So since carbon orbitals are involved in back bonding, the answer is given as what? D. All right. So this ends the chapter coordination chemistry. We have done in detail coordination chemistry. Possibly we'll have one more session. I will see if I can get some other questions and solve the chapter, or we'll go for a new chapter tomorrow. All right. Any clarification? You can get it done, students, now. Any clarification, students?
No, sir.
Yeah. Okay, then we'll wind up. Madam? Madam?
Thank you, sir.
Yeah.
Thank you, sir.
Yeah, bye.